Okay, this is when you actually need to draw some organic molecules. Now, I'm going to go through these. Not all of these you need to know. I'll tell you the ones that you don't need to know, and there are certain aspects of it too that I don't expect you to know as well. And then there are a few in here that I'm not really too sure about myself, so I'm going to make sure that we steer clear of those ones. I only expect you to do the ones that I can do myself. All right? So it's asking you to do these reactions. So we're going to predict the products of these reactions. So it says predict the product of the following chemical reactions and indicate what kind of reaction as well. Okay? The substitution reactions indicate if they occur S1, SN1, SN2, backside or front side attack, inversion or retention of configuration, and whether it is conservative step or stepwise. You do not need to know that. Okay? That's not important. So you do not need to tell me if it's SN1, SN2. That's beyond what we should be able to do for this course. You should be able to tell me it's a substitution reaction. That's reasonable. I expect that. You don't need to tell me if it's a front side attack or a back side attack. You don't need to tell me inversion or retention of configuration. Okay? And you don't need to tell me if it's concerted or stepwise. Okay? But draw out the molecule if needed. You should draw every single one so that you understand the steps. Okay? Am I going to be doing this exactly the way it should be done? No, but I'm going to show you what I expect for our basic introductory chemistry course for what to do. And this will also help you out for also when we go into more detail for AP chemistry, but also for AP biology next year for those that are taking it. For those that aren't taking it, that's why I'm only expecting the basics of this whole thing. Okay. So, 21. All right, so it says one ethene reacts with water in solution with an acid catalyst. So first we should figure these out. We should draw these so that we know what this means. So ethene, what does this mean? It means we've got two carbons, a double bond, kind of looks like this, okay? So H's, believe it or not. 2-ethene reacts with water, an acid catalyst. So we show that it's an acid usually by writing H+. Shows that it's an acid. Not if you just want to write acid, that's fine. Remember what a catalyst is? A catalyst is something that doesn't itself participate in the reaction, and you could remove it afterwards, but it usually speeds up and assists the reaction in some sort of way. So it doesn't participate in becoming one of the products, it just helps it to happen in the first place. Okay, so what we're going to do is we're going to change this by adding something here. Now, remember from that other video about what happens when we want to add something. Usually what we're doing here is we need to break one of these double bonds. So alkenes with double bonds and alkynes with triple bonds are highly reactive because we can break the bond. We need some sort of catalyst to give it a bit of energy, a bit of activation energy, or lower that activation energy to make it easier to occur. But once we do, we can free up bonding spots here to add something. Okay, so what we're going to do is we are going to break one of these bonds and free up a space to add something to it. Now, what are we going to add? So if we think about water, so what is water? So water, we have H2O, but so in other ways we've looked at it when we were looking at balancing chemical reactions before, equations. We saw that it's sometimes easier if we consider water to be hydrogen hydroxide when we were balancing. Just made it a little bit easier to think about it this way, especially when we had other hydroxides in there. So if we think about it this way, what we're actually going to get is we're going to take this OH group and we're going to bond it here. Okay? So what is that OH group? Well, it's an alcohol group. So what we're going to do here is we're going to make an alcohol. Okay? So, see, we're going to break that double bond. Okay. This hydrogen here. So what happens is, from that video, this hydrogen here, water can dissociate in solution to make either a very weak acid sometimes or a very weak base. Not that important. But anyways, it could break apart into H plus and OH minus. The H plus, remember from our video, is what we call an electrophile. That means that it's electron loving, so it's going to be attracted to a highly negative source. So it's going to be, where's the very negative source here? It's this double bond. It's going to be attracted there and break it. And this one is going to attach, and we've got our other two that attach. Okay? When that attaches, that makes this carbon positive, right? It becomes a carbocation, which allows our oxygen to bond here, and then we got hydrogen, hydrogen, like this. So there is our water bonded to that molecule under the presence of the acid catalyst. Okay, so what kind of reaction is this from our list? This is an addition reaction. We're adding the hydrogen and the hydroxide group to the ethene molecule. So what did we make from doing this? What's our product? What is this? Well, we made ethanol. That's what we made. Okay? Okay, let's look at maybe we won't do them all this time, give you a chance just to kind of work through them. Okay, number 2, so we've got hydrobromic acid with 1 propene in solution. Propene, so it tells us we've got another double bond. So, propene, 1, 2, 3, 1 propene. So it's got this double bond here. Okay, and then 1, 2, 3, 4. 1, 2, 3, 1 here, 1, 2, 1, 2, 3. Okay. Okay. Hydrobromic acid, so that's plus HBr. And we're just saying it reacts. So this is an acidic solution. It's pretty strong acid is what it is. So whenever you see it's a double bond, what's going to happen here? This is going to break apart in solution. Make a positive and negative. Okay? This positive is going to be attracted to this double bond. So really what this happens is it's a 2-step reaction. It's going to be attracted to the double bond and break that double bond. Okay? Now the question would be that some of you are asking, and I can hear Noelle and Angeline and Sim and some others asking, how do you know where that, where the hydrogen and the bromine are going to attach? Well, your carbocation, the one that becomes positive after the hydrogen has attached, is going to be on what's called the most substituted carbon. So your carbocation, the positive one, is on the most substituted carbon. What does that mean? Well, it's the carbon that has the most groups that are attached to it, the most other groups. So this carbon only has 1 other carbon attached to it, but this one here has 1, 2. This carbon is the most substituted carbon. So what does that mean? That means that your bromine is going to attach here. This is going to become your carbocation. Okay? So that means that our first step, I don't have enough space there, so after we make it, our first step then will be to break that double bond. I'm just going to write that like that. Break that double bond, got 1 hydrogen here. And that hydrogen from here is going to attach down here. That makes this one positive, okay? Positive and negative are going to attach. That's the first step. See, our carbocation is on our most substituted carbon. Okay, that's, remember that was called Markovnikov's rule, is what that was called. Okay, okie dokie. So what we're going to get next then, this is not complete because we still have our bromine. So it actually occurs in 2 steps, but on your final exam, if you want to draw it in 1 step, that's fine. I don't expect all the intermediates. So 1, 2, 3. This one now is like this. This one has this, and then that bromine comes in and attaches to the carbocation like this. And this is technically what you can call the Markovnikov's product. Okay, this is a kind of, what kind of reaction is this? This is an addition reaction as well. Okay. Maybe I'll go through only about half of these today and then give you some time and go through the half later. Okay. Okay, number 23, 3-methyl-2-hexene reacts with hydroiodic acid solution. Okay, so that's kind of similar to what we had before, but there might be one little difference to it. So we've got hexene, so it's 1, 2, 3, 4, 5, 6, 2-hexene, three methyl, third carbon, 3-methyl, 2-hexene, okay? And it's going to react with hydro plus HI, hydroiodic acid. Okay, again, what does this mean? So in solution, right, this breaks apart, positive and minus. Okay, so the first step is that your positive is going to be attracted where? To a nice source of double of electrons, which means it's going to be attracted to this part here. It's going to break apart that bond. Now, the question is, where does the hydrogen attach and where does the iodine attach? Well, your carbocation, where your negative ion is going to attach, is always going to be on the most substituted carbon. Okay? So, if it attaches here, then this carbon is attached to 2 other carbons. If it attaches here, this carbon is attached to 1, 2, 3 other carbons. So this forms a very stable carbocation. Why? Because if we think about it, these other carbons all have electrons and the hydrogen's attached to, it can kind of share and maybe steal some of those electrons, so it forms, there's more electrons floating around than it could possibly steal to stabilize itself. It's still going to be positive. If it comes here, there are less electrons that are available for it to try and stabilize itself. So it's a little bit less stable. So you always want to try to make the most stable carbocation that you possibly can. And that configuration for the most stable carbocation is always going to be on the most substituted carbon. That's Markovnikov's rule. So we always need to consider that. So what this means is we're going to get carbon-carbon. Our hydrogen is going to attach here. I'm going to circle it just so we remember that that's from our solution here. We still have our 3 hydrogens here. Okay, so this that one of course shouldn't have had that extra hydrogen, or else it would have had too many. So that's got our CH3. This is going to form our carbocation, which is going to be stabilized by our iodine. Okay, that's what it's going to look at like. So, again, this is a kind of an addition reaction. It follows Markovnikov's rule. And what does it make? Well, it makes 3 ido, 3 methyl hexane, if we were to label it. Right, so this is 3 ido, 3 methyl hexane. All right, so we took hexene and we reduced it down to a hexane. We took an alkene and we reduced it down to an alkane so that we could add a halogen to it at the double bond. I don't want this to go on too long. Do one more. We'll do one more and leave it there, and then I'll tell you the ones that you don't need to know and the ones that you should really look at for your exam. Okay. So 24. 24 says I have 2 ido propane. So that one's a hard one. 2 ido propane reacts with potassium hydroxide solution. So let's draw propane. So we got 1, 2, 3 carbons for propane. It says 2 ido, which means I've got an iodine group attached to it. And then additional H, and I have an H. Okay? And it's going to react with potassium hydroxide. Okay. So this in solution is going to break apart into the potassium ion. This is going to break apart into the hydroxide ion. Okay, so what do you notice? So first of all, do we have any double or triple bonds? No, we don't have any double or triple bonds. So this is not as reactive. But what can happen here, what's going to happen is we're going to substitute. This is a kind of substitution reaction. So what happens is our hydroxide group is going to come along and it's going to kick out this halogen. So we get one that's going to kick it out. Our potassium ion, there's no good source of electrons anywhere here to get it really, really interested in anything here. So it's not going to come apart. But what we're going to do is get this one to come apart and attack it. Now, what will happen is, if you want to know, it will come in from the back to attack it. Because if it comes into the front, this is very negative, it's going to repel. You do not need to know that for this question. You need to know that this, what's going to happen is you're going to get 1, 2, 3. And this is not exactly the right answer, but just so you know, this OH group is going to come in here. You're going to make an alcohol. You're going to make 2 propanol out of it. What kind of reaction is it? This is a substitution reaction, meaning we took one out, we kicked out the iodine. The part that's kicked out, we call that the leaving group. So we kicked out the iodine and we replaced it with an hydroxyl group. I think if you want to know technically, this hydroxyl would be in the back, but we're not really, with our drawings here, respecting molecular geometry. That's for another course. Okay, but that's basically what happens there. That's at about 20 minutes, so I'm going to leave you to try and look at these. No, actually, maybe we'll do one more quickly. Okay, and actually the one that I want us to look at quickly, I put a star next to it, that we can do is 26. And I'll tell you why we need to really look at 26 and consider it to be important. Okay, so we've got ethanol. We've got ethanol, F, 2 carbons, OH, okay, you've got ethanol, and it's going to react with butanoic acid. So but has 4 carbons. Butanoic acid means this an organic acid. It looks like this. Okay. For your exam, you should label them too, which ones they are. So this is ethanol, and this one is butanoic acid. So we're going to take these ones together, add them together. Now, we've talked about this one before, quite a few times. This one we've got an alcohol and we're adding it to an organic acid. When we add an alcohol to an organic acid, we make an, is it an ester or an ether? We make an ester. Right. So, let me check. Yes, ester. I'm always afraid that I always get ester and ether mixed up too. So ester, yes, and ether just has the bridging oxygen. So an ester. So we're going to make an ester. And this is a big one that you need to know for your exam. So, start with your acid group first, is a good way to do it. So, 1, 2, 3, 4. Okay, you're going to have your double bonded oxygen, and then you're going to have an oxygen here. Remember, this oxygen doesn't come, it comes from, actually it comes from here, it comes from the alcohol. What you're going to do is you're going to have this oxygen come off and these come off, and you're going to get some water that's formed as well, H2O. Okay, then you're going to have your 2 like this. What does this make? So this makes, so we talked about the alcohol group first, so this makes 2 carbons, so this makes ethyl. And then 4, we've got butanoate. That's what that makes. Plus, of course, plus we get some water coming off at the end too. Ethyl butanoate plus water. Okay, this is a good one. You should practice this one. You need to know this one. Okay, that's a good one. Now, I've labeled this. 28 is something called a redox reaction. We haven't studied any redox chemistry, so I do not expect you to do 28. Also, the other one that's a bit confusing, 37 actually has no reaction with it, and it's a little bit hard to go through the reasons why. So 37, please forget about that. So 28 and 37 you do not need to worry about. Any ones that look like they have an alcohol and organic acid, again, I strongly suggest that you study them for the exam. Okay, I'll work through more of these examples a little bit later. The next video that will come out will probably have a discussion about organic molecules and boiling point.